Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever with part 2 of logarithms. Let's get to it, shall we? All right, so we left off with example 26. Let's work on example 27, shall we? We are going to write these these equations without any logarithms, and all we're doing is we're gonna use our rules of logarithms. So I am going to say that this is equal to log A plus log B cubed, and I'm using this exponential law right here. And then, since this is addition, I can then write this as log of AB cubed, right? And I guess I should have been writing log C here all the way down. Well, if log of C is equal to log AB cubed, then C must be equal to AB cubed. Hopefully that is intuitive for you and it is obvious. Okay, so now we have log G, and I'm just going to manipulate the right-hand side here. I'm first going to write this as log D squared, and my goal here, I have to write this right side as a single logarithmic term. So, from the previous video, I know that I can rewrite this as log of 10 to the first power, because log base 10 of 10 is equal to 1 for sure. So now I can say that log G, using my subtraction rule here, is equal to log of D squared over 10. Last time I checked, 10 to the first power is indeed 10. So therefore, G must be equal to D squared over 10. No questions asked. Okay, so onward we go. Logarithms and other bases. So take a look here. If 10 to the x equals b, then x equals log base 10 of b. And this is what I like to say, coming home to mama. Whenever you get in trouble, a lot of times all you have to do is convert from exponential to logarithmic form, or from logarithmic form back to exponential. So write an equivalent logarithmic statement for 3 to the fourth is equal to 81. So, you know, if you want to, before you get used to it, 3 to the fourth, 81, it's a pretty easy, it's fairly intuitive that we would know that 4 is equal to log base 3 of 81. And that's because 3 to the fourth power is equal to 81. Kind of like this circularity thing. Yes? So there we go. All right. What else have we got? Final thing, graphs of logarithmic functions. So if I consider x equal to the 2, x equal 2 to the y, that is only true if y equals log base 2 of x. Okay, and we know that 2 to the y is greater than 0 for all y. Think about that. There is no value of y that is going to give you a negative number. It's just not possible. And we talked about that in the previous video. So we know that the domain is all reals greater than 0. It also can't be equal to 0. So that's why it's not greater than or equal to. You can make a table of values and you get this nice little graph there. And we're always going to cut the x-axis at 1, 0. Another way to think about it is a nice little drawing here. Let me get rid of this. So if y equals log base 2 of x, that's only true if x equals 2 to the y, which we've established up here. But if you think about the inverse, what is the inverse function for x equals 2 to the y? Well, it's equal to y equals 2 to the x power, which is a graph we are familiar with. It's right here, yes? And recall that the graph of the inverse of a function is reflected in the line y equals x, right? Now, again, the inverse of y equals 2 to the x is x equals 2 to the y. So that is another way to think about what the graph of y equals log base 2 of x is, because again, it's equivalent to x equals 2 to the y. Again, that's just another way that you can think of the graph of a logarithmic function. Okay, hope you enjoyed it. I certainly did. Let's check out how the tunes are going. And before we sign out, that is the end of logarithms, or no, of the logarithm videos. And with that, I am going to say that I am out.